Hi there, and welcome to Raelene Math. Let's take a look at three important functions that have holes at x equal to 0. Without these functions, we would not be able to figure out the derivatives of sine x, cosine x, and e to the x. But the functions themselves are not sine x, cos x, and e to the x. They are slightly different. First of all, they all have a domain of x contained in the reals except for 0, because the denominator can't be 0, and x therefore can't be 0. So we do have holes in these graphs. And the first function, the hole is at 0, 1. In the second function, the hole is at 0, 0. And in the third function, the hole is at 0, 1 again. So let's take a look at the first function. F of x equal to sine x over x has odd symmetry because f of negative x is equal to the sine of negative x over negative x. Each of these functions is odd. And when we simplify negative sine x over negative x, this gives us the original function sine x over x again. And so when a horizontal reflection equals the original function, we have an even symmetry function. And so that means that we can consider a mirror image through the y-axis. It turns out that when we take a look at x approaching 0 from the right on the graph, y approaches a height of 1, and by even symmetry, as x approaches 0 from the left, y approaches a height of 1 still. And when we take a look when x is 0, we see that y is sine 0 over 0, which is indeterminate, 0 over 0. This is indeterminate because the y value equal to 0 over 0 is the solution to the equation 0y equal to 0, for which there are infinitely many solutions. And so y fails to be just one height on the function when x is 0. And as a result, the y value on the function doesn't exist. So we remove this point. We have then that the limit as x approaches 0 from either the left or the right-hand side on this graph of sine x over x is equal to 1. But because the function value when x equals 0 does not exist, even though the limit value does exist, we say that f is not continuous at x equal to 0, and the graph has a hole at 0 for x and 1 for y. Those values are coming from here. That's the x-coordinate of the hole, and this represents the y-coordinate of the hole. In other words, the value that the limit equals represents the y-coordinate of the hole. So if we take the function sine x over x and we add a table, I'm going to type in sine of x1 over x1 here. I'm not typing anything interesting or special, just x1. And so let's put some x values, say going from pi towards 0. So let's type in pi and we get the x-coordinate gives the y value of 0. And then we can take 3, let's take 2, that should be 2, 1, 0.5, 0.4, 0.3, 0.2, 0.1. We start to see that the y-coordinates are getting closer to 0.99 now. And what happens if we zoom in and get even closer? 0.01, 0.001, and so on. Well, at this point, it suggests that when x is 0.0001, that y is 1. But that's not entirely true. It's just we don't see enough of the decimal points here in the Desmos calculator. But we can see here that as the orange points, I'm going to change the color to make them a little bit darker. Maybe the black points will show up. As the x-coordinates are moving from pi towards 0, as x approaches 0 from the right, the heights of the graph are getting closer and closer to the height of the graph y equal to 1. And so we say that as x approaches 0 from the right, y approaches a height of 1. And the same is true coming from the other side by even symmetry or just plugging in numbers into a table of value. So we have indeed that as x approaches 0 from either side, y approaches a height of 1. The limit exists even though the function value is not defined and we have a hole. The second function to take a look at is not the cosine x graph, but another function that is indeterminate at x equal to 0. So we have a 0 in the denominator, and cosine of 0 is 1, subtract 1 gives us 0 over 0. Again, the y-coordinate is trying to take on infinitely many coordinates here, and so in order to preserve the function status of this graph, we have to remove the point that it looks like we would have. What's really going on is when x is equal to 0, we have y solving this, which is going to be infinitely many solutions. And those infinitely many solutions could be things like y equals 0, or y equals 1, or y equals 2, etc. And so y ends up being an infinite number of heights on this graph. We don't want y to be any of them, so we take those away, and we need to make sure that we take away the point when y equals 0 as well. Okay, in this case the function f of x has odd symmetry, and if we replace x with negative x, we're performing a horizontal reflection here. We see that the numerator, cosine of negative x, is the same as cosine of x because cosine's symmetry is even. And so the numerator of the horizontally reflected graph, when we replace x with negative x, is the same as the original numerator, but the denominator is the negative of it. So overall, we have that this function is equal to negative times the original function, which is negative f of x. And so we see that performing a horizontal reflection on the original graph is equivalent to performing a vertical reflection on the original graph, and so the function has odd symmetry. However, as x approaches 0 from the right, y approaches a height of 0, and as x approaches 0 from the left, y approaches a height of 0. And so that we get, regardless of the direction x approaches 0 from, on the graph of cosine x minus 1 all over x, the height of the graph is approaching one single height. It's a finite number, and that value is 0. So the limit value exists, and we have, since f of 0 does not exist, taking these two things together, we have a hole at the x-coordinate of 0 and the y-coordinate of 0. The third special case that we want to look at is the e to the x minus 1 over x function. It looks a lot like the function of e to the x, and so we can actually compare those two functions. Take away some of these other pieces of information, and looking at the e to the x function, we get an exponential growth function. And then looking at this similar function, e to the x minus 1 over x, we can see that they share some information. They have the same left end behavior and the same right end behavior. Particularly if we zoom out, we can see a little bit better. But they're not the same graph. And in particular, it looks like they share a point at 0, 1. However, on the red graph, we know there's no domain restriction, but the blue graph has a denominator, and so there is a domain restriction. And when x is 0 on the blue graph, it says here that the y value is undefined. Specifically, undefined means not real or not single or not finite. And in this case, the y-coordinate is trying to take on infinitely many values. So we see again the y-coordinate f of 0 in this case is going to be e to the 0, which is 1 minus 1 all over 0 is 0 over 0. So the y-coordinate is indeterminate, which is a specific kind of undefined. It's undefined where the y-coordinate fails to take on or equal a single value. In other words, the solution to 0y equal to 0 fails to have just one single solution. So y fails to be a single value, and therefore the type of undefined specifically is indeterminate. There's no symmetry here. We saw that as x approaches negative infinity on this blue graph, we can see it again here, that y approaches a height of 0, which by the way says we have a horizontal asymptote at y equal to 0. And as x approaches positive infinity, as we look at the right end, the right side of the graph, y approaches positive infinity. So we don't have any kind of symmetry going on here. We have very different end behaviors. But specifically looking at the graph, as x approaches 0 from the right, y approaches a height of 1, and as x approaches 0 from the left, y approaches a height of 1. So we say that the limit as x approaches 0, regardless of the direction, left or right, on this graph we have that y approaches a height of 1. And taken in conjunction with f of 0 not existing, because y was indeterminate because we got 0 over 0 for the function value, we can say that this function has a hole at 0, 1. So these three limits are really, really important when we move on and we use them in the limit definition of the derivative, the instantaneous rate of change. Here is a summary, a rule of 4 summary in terms of the algebra, the graph, the numerical, and the verbal description or representation of these three graphs. And if you like the video, let me know. Also, tell your friends, and if you haven't already, please, I would love it if you subscribe. Thanks for checking out Raelene Math.